welcome to this explainer. Okay, we've got a truly fascinating piece of wireless history to decode today. We are going to step inside the FPGA that quietly became cutting-edge battlefield tech. We're going to untangle some incredibly clever high-level engineering, and we're going to trace a straight line from what was basically an obscure academic paper directly to a multi-billion-dollar corporate buyout. It's an amazing story, so let's just dive right in. We absolutely have to start with this number right here, $4.4 billion. That is a staggering amount of money, and it's the exact price tag paid by Motorola Solutions back in August of 2025 to acquire a tactical communications company called Silvus Technologies. Now, this was a massive deal, totally driven by the modern military's need for ultra-reliable, infrastructure-free comms. Think everything from ground units to autonomous drone swarms. But here's the kicker. The technology that anchored that historic billion-dollar acquisition, it did not start in some flashy corporate R&D lab. Contrast that massive military tech buyout with its actual, very humble origins. This whole thing traces back to a 2007 academic paper presented at a signal processing conference over in Poznań, Poland. It was authored by a team from UCLA alongside a then-tiny side venture called Silvus Communication Systems. And look, it didn't make mainstream headlines. It was just a dense, math-heavy PDF about a radio board. But as we're going to see, this document was basically a crystal ball. It was a blueprint for the future of tactical wireless networking. This chunky piece of lab hardware is basically the Trojan horse of our story. It's a physical prototype built into a 17-inch CPII chassis with those 4 protruding antennas. Now, they didn't build this to sell to the military right out of the gate. Actually, scratch that. Military applications weren't even the immediate focus. They built it to solve a massive, incredibly frustrating bottleneck that was plaguing university wireless research at the time. So what was that bottleneck? Well, researchers desperately needed a way to test real-time network behavior. If you wanted to see how a network reacted to interference or fading in the real world, you were kind of out of luck. You either had to buy closed commercial Wi-Fi chips, which are basically black boxes where you can't see or change the internal logic, or you had to use what they called store and process systems. Those would record raw radio signals out in the field, and then you'd have to lug them back to the lab to process them offline on a computer. And honestly, that's completely useless if you want to test how a live, two-way connection reacts dynamically. They needed a self-contained, real-time radio that they could control from the ground up. To really appreciate the solution they engineered, we've got to briefly define the underlying tech. The first half of the puzzle is OFDM, or orthogonal frequency division multiplexing. This is the resilient backbone of modern high-speed wireless. It's exactly what your Wi-Fi and 5G networks use today. Instead of blasting your data over one single wide frequency, OFDM acts like a multi-lane highway. It slices your data across multiple, narrow, tightly packed subcarriers, which makes the overall signal highly resistant to interference and echoes. The second half is MIMO, or multiple input, multiple output. This is where this hardware brilliantly leveraged those 4 antennas we saw a second ago. MIMO uses multiple antennas at the exact same time for 2 very different tricks. First, you can send the exact same data over multiple paths so that if one path suffers a bad signal fade, the data still gets through cleanly. Or you can do spatial multiplexing, which means sending entirely different chunks of data across each antenna simultaneously to literally multiply your data throughput. And the true power of that spatial multiplexing becomes super clear when you look at the raw numbers. Say you have a standard single antenna, a 1x1 setup. You might push, 52 megabits per second. But by jumping up to a 4x4 MIMO setup, using 4 antennas on both sides to transmit different data streams in the exact same frequency space, they effectively quadrupled the throughput to a theoretical 208 megabits per second. But here is the crucial takeaway. Raw speed wasn't the ultimate goal here. This hardware gave researchers over 300 unique operating modes to experiment with. Bandwidths, constellation sizes, coding rates, antenna configurations. Every single element could be swapped and tested. It was an absolutely unprecedented sandbox for wireless engineering. All of that flexibility enabled something totally revolutionary at the software level. The team built an API that allowed the higher networking layer, the software actually making the decisions, to completely reconfigure the physical radio parameters in real time. And they didn't just do this for an entire session. They did it packet by packet. Imagine that. Every single data packet could be sent using a completely different modulation, coding, or antenna setup based entirely on what the network needed at that exact millisecond. Now, to make a radio that fast and that flexible, you can't just rely on standard off-the-shelf processors. The entire baseband processing for all 4 antennas, the actual digital brain of the radio, was crammed onto a single field programmable gate array, or FPGA. Specifically, they used a Xilinx Vertex Second 8000. If you don't know, an FPGA is a chip where you literally configure the physical logic circuits yourself to do exactly what you need in parallel at blistering speeds. It's like digital clay. But molding that digital clay brought up a massive mathematical hurdle. When you receive 4 separate data streams overlapping on the exact same frequency, you have to untangle them instantly. The team chose a MIMO detection method called linear MMSE to do this. But here's the problem. The textbook version of this algorithm requires directly inverting a complex matrix. In the fixed point math of actual hardware, matrix inversion is a total nightmare. It's highly unstable, and it breaks down exactly when your signal gets messy. So, the engineers cleverly reformulated the math using square root MMSE to completely bypass that unstable matrix inversion. But, as is always the case in engineering, fixing one problem created another. Their solution required a heavy computational step called QR decomposition. And picking an algorithm to solve this wasn't about textbook math anymore. It was about managing physical real estate on the silicon chip itself. The standard method, called Givens rotation, required specific hardware circuits called Cordic operators, which would just eat up way too much of the FPGA's limited space. So they had to pivot to an alternative, called the modified Gram-Schmidt method. And this is where they got really clever. By leveraging the built-in multipliers that were already just sitting unused on the FPGA, instead of forcing those bulky Cordic operators, they totally optimized the Gram-Schmidt method. By mapping this directly into the FPGA's internal memory and FIFOs, they managed to run highly complex, mathematically stable MIMO decoding without overflowing the chip's capacity. Honestly, it is a perfect example of brilliant hardware-aware engineering. So, once all that intense math was finally baked into the silicon, it was time to test it. And the lab results? They were virtually flawless. They proved the hardware could seamlessly swap between 13 different configurations on the fly without ever breaking the connection. They even ran live movie and file transfers, proving the system could autonomously detect dropped packets and retransmit them, the whole ACK/NAC protocol behaving exactly like a real-world commercial network. Okay, this next detail is hands down my favorite part of the entire story. Take a look at the custom graphic user interface they built for these field tests. Right there, sitting next to the real-time constellation graphs, are literal silhouettes of a military tank and a helicopter. Even way back in 2007, while they were doing university-level testing alongside a map of the Los Angeles freeway, they were perfectly foreshadowing exactly where this technology was destined to go. And to truly prove the system's ruggedness, they packed it all into a car for the ultimate stress test. Driving this prototype onto the busy freeways of LA, they proved the system could dynamically self-heal its connection through rapidly changing environments. They successfully sustained a rock-solid 10 megabit per second connection while cruising at 70 miles per hour. That kind of rapid, high-speed fading is incredibly difficult for radio to process, and their FPGA handled it without breaking a sweat. So here is how all those dots finally connect. One of the co-authors of this paper, Dr. Babak Danisrad, took this exact foundation of real-time self-healing MIMO research and poured it directly into his company, Silvus Technologies. Over the next couple of decades, they refined this tech into the Streamcaster series of tactical radios. We're talking devices that provide critical mesh networking for the military in the absolute harshest environments imaginable. And that direct lineage, right from a 2007 academic testbed, is exactly what culminated in that mind-blowing $4.4 billion Motorola buyout in 2025. Which leaves us with a truly fascinating question to ponder. We just traced a multi-billion-dollar tactical revolution back to a single, dense academic presentation about FPGA resource allocation. So, as you look across the vast landscape of modern research being published today, what other battlefield technologies or totally industry-defining breakthroughs are quietly waiting in an obscure PDF on a university lab bench right now? Thank you so much for joining me on this explainer. I really hope you found this deep dive as fascinating